Good day everyone, and welcome to our webinar on the subject of design and model drainage storage structures. My name is Peter Coombs and I'm here with my colleague Ludmila Fadeva. So we're here to run through this webinar, fairly brief one today, go through some theory on the design of storage structures based on the new guidance that's been sent out fairly recently, the SuDS manual, and I'll give you a very quick demo at the very end to show particular subject I'm going to focus on today, which is actually thinking about the flow of the runoff, not just entering into the structure, but through the structure itself. So this is something that's started to come through with the advent of the SuDS manual. So I'm not sure if people have been asked to do this yet. I'll be very interested to receive your feedback. So I'm here with Ludmila, and if you have any questions or feedback, then feel free to sort of send those questions down the line. We'll either attempt to answer them during the course of the webinar. You'll see this in the little pop-up box that you have there, or we'll answer them at the very end and send out a separate sheet. So the plan is I'll run through the latest SuDS guidance, and as I mentioned, I will focus on one particular area, and that is looking at the flow through structures, FTS, yet another acronym for us to remember, and the multiple benefits that this will bring to us with our design of sustainable drainage systems. I'll then run through a live demo and show how I've designed a flow-through structure, and I've chosen the most difficult one, which is a bioretention area, and how we can incorporate that into our models in MicroDrainage. So I'll run through that a little bit towards the end. Just as a reminder on what we're trying to achieve at a sort of high level with the SuDS manual, Series C 753, we now have the 4 pillars, and this is covering the water quantity, the water quality, the amenity value that we're providing with our designs, as well as enhancement to biodiversity, creating nice places for people to live in. All of these aspects are covered when we start to look at the greener of the infrastructures. The problems, I understand, obviously, are finding the space for such structures. So I've chosen the bioretention area because we can pretty well slip these into any small spaces, and they will all have a cumulative effect and help us with our designs. So the bioretention systems are covered in Chapter 18 of the SuDS manual. And what is a bioretention system? It doesn't have to be a huge thing. On the front cover here, we can see a pond on the bottom right-hand corner. It doesn't have to be a huge structure, actually. It is a shallow planted depression in the ground. Within that shallow depression, runoff will form a temporary pond on the surface, and then the water will go from the surface and filter through vegetation. So it's typically a vegetated depression in the ground, and as that water filters through the vegetation, it'll get into the underlying soils, and those soils themselves will either collect and provide some kind of a volume under the ground, depending on the nature of the filter system or systems that we have below the ground, and that water could infiltrate or maybe not into the ground. So we can either use them for attenuation or for infiltration as well. This is a typical example of what we're looking at, a sort of generic example. They're typically fairly shallow, so in the really open spaces, if you had the room, then we could put in some nice side slopes. I'm just thinking now, if we had areas of public open space, for example, that we wanted to utilize, we could put a depression in the ground in the public open space. Maybe there's lots of room, so we could put in some nice side slopes here on the left-hand side. They would typically be no steeper than 1 in 3, so you go 1 in 3, maybe 1 in 4 on the side slope. Vegetate the depression. The depressions are often fairly shallow, but can be deeper, and there is no kind of one-size-fits-all with this. Below that depression area, you have this sort of shallow ponding effect. Now, where you're in a very tight, high-dense situation, maybe it's a new housing development or something like that, or a commercial location, a commercial development, we could put in some hard edges that will restrict the actual take-up, the land take of the bioretention area. So they don't have to be soft edges, they can be hard edges. And this has been used a lot, particularly in the retrofit industry, which is why I'm going to sort of focus on this particular aspect during the webinar today. So the water forms this shallow depression. It's really great for regular rainfall events. Within the UK, for example, the majority of the rainfall events are less than 5 millimeters in depth. So often that water will be taken up by the vegetation, sit on the surface, and often just evapotranspirate away. Some will seep down into the subsoil, and we put in a filter media down below. So down below this shallow depression, we would put in a layer or layers of filter media feeding down to a drainage layer at the bottom. They don't have to be particularly deep, and this drainage layer would comprise of a bedding stone and maybe a perforated pipe. It may or may not have a pipe to discharge away. If it doesn't, maybe we have the benefit of infiltrating down into the subsoil below that if the conditions are right. We could put in an overflow pipe, a vertical overflow pipe here. So when the design is exceeded, the water could then overflow and then directly enter into the underground drainage system and get piped away. And as I say, these can be added in or maybe not, as the case may be. So there are various permutations that we can take a look at. This really brings me into the MDSuDS module, and the reason and the rationale why we've brought such technology into the MicroDrainage suite now is to enable people to actually design such structures and not just look at the runoff coming from the catchment and entering into the structure and looking at the volume in the structure and then the discharge rate going out. This could be through a pipe or a flow control, but we're actually starting to analyze the filtration rate, the speed of the flow from the surface through the filter media to enter down to the lower layer, and as I say, either infiltrate into the ground if it's a continual process, or maybe getting piped away through some kind of flow control. And here are the kind of key characteristics of such a system. We're looking at these side slopes, as I say, where we have the space. There is another slope characteristic, which is along the length of the bioretention area. Typically, I'd like to put this in absolutely flat or with a minimal slope. And you see areas of sort of ponding, and that will build up, obviously, depending on what kind of return period we've designed these for. And then down below, we have these different layers of filter. And they can be 2, 3 different types of media that we look at. I'll show you one that I've designed, and in true Blue Peter fashion, I'll show you one that I've done earlier. And you have the length, but also you have the surface area and the perimeter of these things. Now, with the source control module, we can design bioretention areas, but we can more visually represent such areas using the MDSuDS module with a CAD drawing. So this is why I'm choosing to show you how to do it with the MDSuDS module a little bit later on. So coming out of Chapter 18 of the SuDS manual, what are the benefits of bioretention areas? Well, they can certainly help us to reduce those runoff rates. They can help us to reduce the runoff volume. They provide excellent interception, as I just already mentioned, those kind of regular rainfall events where we can intercept the runoff for those less than 5 millimeter kind of conditions, and it'll handle within the basin itself and have nothing positively discharged possibly into the positive drainage system under the ground. But also we're satisfying those other pillars coming out of the SuDS manual. We're providing water treatment because of the filter layers down below the surface. Treatment because of the vegetation actually on the surface even before the runoff is filtered down below. We're also providing super amenity value in terms of the greenery, the green infrastructure, and an enhancement to the biodiversity as well. And as I've mentioned previously, with the soft edges, we can use those on the relatively low density developments where you have the space with the 1 in 3, 1 in 4 side slopes. Or if you're restricted on space, there's no reason why we can't try to incorporate such things, but with hard edges to restrict the land take. And it's the use of those hard edges that have been used so successfully in retrofit schemes, which is another reason why I want to sort of share the opportunity of maybe utilizing more greatly bioretention areas in the future. Welsh Water, Dir Cymru, have invested a lot of money in such retrofit schemes, £50 million actually, in Llanelli and Bioretention areas, under the banner of the Rainscape projects. And on the right-hand side here, we can see some examples of those projects that have taken place. The bioretention areas are not unique. We've used swales, porous paving, below ground storage, grassy channels, as well as bioretention areas all over these places. So it depends on the location, on the situation, as to what we can kind of best fit in. But the benefits from the Rainscape projects that they've attributed are a reduction in sewer flooding. So what they've been doing very successfully is taking surface water out of the combined sewers. They've reduced the amount of sewer flooding, and therefore a reduction in pollution coming out of such situations as well. They've created more green spaces, and I know this is showing a fairly new development in grounds, but there's a lot of Victorian terraces as well, where retrofitting has taken place within very restricted sites actually. But they've created some nice new green spaces, some new habitats for wildlife to exist, and overall it's improved water efficiency, as a lot of the rainwater can be recycled and then reused for sort of green for purposes such as gardening and toilet flushing. Wouldn't use it for potable water, but for those purposes it's great. So the main functions and the main elements of bioretention systems are the inlet, so the inlet kind of condition where the runoff is entering into the structure. The fact that we have an extended detention time, a delay time of that surface water runoff at the surface in the depression. We also have vegetation, and then below that vegetation, below the soil, we have filter medium. There's a transition layer below that medium, such as the geotextile, before we have a drainage layer, so the pipe bedding, open stone with maybe perforated pipes or not, as the case may be. And on occasion we can put in overflow as well. So these are the kind of main aspects, all in the one structure. There are a great variety of them. So when you mention bioretention systems, it's a bit of a generic term. So I could be referring to such a thing as a rain garden. And there are examples within the Syria manual, the new manual. Here's a downpipe on the top graphic here, a downpipe coming off the roof, going across a grassy slope and going into the ponding area, filter media below and infiltrating into the ground where appropriate with some kind of an outlet. Issues that we'd have here, a couple of things. We need to typically be 5 meters away from the property. So it wouldn't be for the sort of smaller properties with small front gardens and things like that. But here are some examples in photographic form of where they have been put in to front gardens. Here's a construction shot of one being built here, and then the finished job shown on the bottom right hand side. So they can be, and typically are, relatively small scale structures, but can be interlinked between one another. We can include bioretention tree pits. So throughout the public highway, here's an example from Portland, Oregon. So many thanks to Sue Illman of Illman Young for the photographs that have gone into the SuDS manual here. These can be fitted into most areas, and they have been fitted into the Llanelli Rainscape projects, but in the public highway. Yes, some people don't like the fact that they've lost a car parking space, but they add in traffic calming, they add in greenery, and reduce the heat in the heat gain in the summertime with such tree pits that have been planted. There are some proprietary tree pits that can be actually purchased nowadays as well. They don't have to be sort of naturalized and planted out. There are tree pits that are already custom made for you. We could look at a bioretention swale, so a longer structure, a longer linear structure. And the other thing that I'm interested in here is not necessarily introducing the flow right at the upstream end of this swale as a runoff from the development, but the lateral flow coming in off the highway as we come down along the swale. I want to better represent and model and design with the lateral flow running across this grassy strip and then entering into the bioretention swales. So down beneath this swale, what's the difference between this and a regular swale? Well, down beneath this, you will have the filter media and potentially a pipe network as well. There's also such a thing as an anaerobic bioretention system. Now, this is really great where you have maybe a lack of water, actually, where we're deliberately putting in a system such that it will retain water at the bottom. We're going to retain standing water in the bottom of the pit. There will be an outfall that's set at a slightly higher level, but maybe we're going to build in a pit or a sump with 300 millimeters or 600 millimeters depth of permanent water, such that the vegetation can survive through periods of drought and things like that. And possibly more important as we start feeling the effects of climate change in the future for maybe longer, fingers crossed here, for a longer, hotter, dry spell as we get towards the end of spring and into the summer period of time. Maybe wishful thinking, but these are ways that we could maybe start to mitigate against drought situations in the future. Again, we have vegetation on the surface, side slopes or hard edge could be introduced here. The filter medium, transition layer or geotextile to prevent fines from migrating through from the filter medium down into the drainage layer. We don't want them clogging up. And then we have the standing water within the drainage layer and then an outfall coming away. All of these different things could be designed and modeled within the MDSuDS module. If we step back a little bit and look at the general design considerations, there's a paper produced by Davis in 2008, and this was to suggest that generally we shouldn't be putting areas in that are greater than 0.8 hectares. So typically the areas are 0.8 hectares or less in area, running off into the bioretention area. The surface area would typically be only 2 to maybe 4% of the site area. And the idea is to link several smaller areas together to gain the multiple benefits of these all interlinking. They're designed for these intermittent rainfall events, so they're generally quite shallow. You could just have a 150, maybe 200 millimeter depth of water for, say, the 1 year return period, and then have a 500 millimeter depth on the surface for, say, the 30-year return period. It depends on what you're being asked to design in accordance with by your approving authority. So I'd encourage you to talk to the water companies. I'd encourage you to talk to the local authorities, the flood risk managers, and the Environment Agency at the outset of the design to get an understanding of their needs in the local area. And they are suitable for most soil conditions. So we can put them into clay soils and pipe away. We could infiltrate into the ground if we're in areas of alluvial deposit. The very steep sites, you may have issues. It's still kind of feasible, but you may have to offset the cost of putting something in that as I mentioned, I'd like to have that in virtually horizontally rather than with a great slope. I don't want this scouring out. There have been some bad experiences in Australia. They've used these an awful lot actually in Australia, and there's been both good and bad experience there. So we've learned a lot from their experiences over there. And the other thing is the top ground water level, TGWL, the top ground water level below the invert level of the filter media should be at least 1 meter below the invert level of the bioretention system. And we also need to be aware or beware of any contaminated runoff. These systems are really great for providing treatment and for rainwater harvesting. So good for things like highway diffuse pollution, for example, but they won't remove pathogens. So if you did need to remove pathogens, we'd have to put in some form of sort of disinfection prior to reusing that water. But they are really good for water quality. That being said, if we put this right alongside a lorry park and you had a lot of highly polluted runoff coming down through into it, and we then infiltrated into an aquifer, you'd have to be careful, and we'd have to maybe have a forebay area and have the opportunity to be able to sort of cut things off if there was a kind of pollutant load that hit us through a lorry tank bursting, or yes, high concentrations of pollutants coming off of such an area. When we come to selecting and siting them, as I mentioned, they're applicable to most type of development. They're a very cost-effective retrofit option. This has been some of the experience coming back from the Rainscape project that Welsh Water have very well done in South Wales. The sizes of the structures, they're saying typically 600 millimeters width minimum would be good. These are not hard and fast rules, but just good guidance. Maximums, we're looking at sort of 10 to 20 meters wide maximum, depending on the maintenance plant, really. So if you had some kind of a reach issue with your excavator, if you did have to dig the thing out at some point in the future, I'd base that kind of width upon the maintenance, looking further ahead now to the maintenance side of things, maybe 10 meters or 20 meters, whatever your plant is that you're working with, as in mechanical plant. The maximum lengths, they're saying 40 meters is a reasonable kind of a figure, and the maximum areas of 800 square meters. So this is why I want to use the MDSuDS, because all of these different kind of parameters are coming out of using that particular piece of software. We can identify all of this and ensure that we're not going like wildly beyond these kind of general recommendations. In terms of hydraulic design, what we need to be mindful of is the maximum velocity of the flow coming in. Again, a good reason to put this in flat and to have kind of side slopes here or a hard soft edge. We don't want to suffer from scour, so we need to restrict and reduce the velocity of the flow, certainly in the ponding area, to less than 0.5 meters. That should be meters squared per second there. Sorry, folks, there's an error in the in the slide there. So ideally, have this longitudinal slope being horizontal as well as crossways. The tension depth, that's usually between about 150 to 300. Could be deeper. Could put it in 500 millimeters, as I mentioned before. There is extra storage to be gained. So we have 100% void in the ponding area up to ground level here. But then we have additional storage within the filter medium down below. And that would depend upon what that medium is. Is it sand? Is it coarse sand? Are they open gravels? So there would be porosity values associated with all of that. And also, it depends upon the permeability values of these filter medium as well as to the hydraulic resistance. So in other words, how quickly will the flow come from the depression storage on the surface and then filter down? What's the filtration rate, the hydraulic conductivity down through towards the bottom drainage layer at the base here? So they're going to have some sort of resistance through those layers. We're going to deposit pollutants on the surface that are basically treated by the vegetation. So the planting out is important here, but we'll treat at the vegetation level, and then the smaller pollutants will get filtered out as we go down through the filter medium down towards the bottom. We want to detain, as I mentioned, for the 1 in 1 year on the surface, typically 150 mil deep, and then up to say 500 millimeters for the more extreme events like the 30 year, maybe the 100 year. And the system should drain down and dewater between about 24 to 48 hours in case we get another rainfall event coming on the top of a previous one. We want to have that sort of half drain down time. We provide interception due to the evapotranspiration and that infiltration potential where it's feasible. So we have great interception values, and it helps to reduce those peak runoffs and the peak volume of the runoff from the site as well. We also need to provide exceedant routes for those events that go way beyond the design. So I'd go for the 100 year, I'd add in climate change, and now we're looking at surface water management. It's not the design of the structure now. We're looking at handling the surface water way beyond the design and taking that flow safely away from properties and maintaining the infrastructure of the development whilst that flow is being taken away. Mentioning treatment, in the demonstration and during the presentation today, I haven't focused on the quality of the water. I'm going to do that in subsequent webinars, I'm focusing literally on the quantity, the size, the siting, and those kind of aspects. And then what we can do is we can build up a treatment train with a number of these, and we can start looking at the different pollutants and the benefits that bioretention systems will provide us. And we can see here from the FAWB guidelines that we have pollution removal characteristics for total suspended solids, phosphorus, nitrates, heavy metals, etc. So we've got known figures that are coming out that are in table 18.1 of the SuDS manual. So have a look at chapter 18 and read up on this after the webinar. In terms of treatment design, they are very effective and very functional. As I say, apart from very high risk areas, they're great at removing sediments on the surface through the vegetation and the ground cover. Those finer particulates and the contaminants will then be removed by the filter media down below. You can also remove some of the dissolved pollutants through that filter media as well. So there are added water quality benefits over and above what we've normally kind of used in terms of ponds and swales typically. And the plants that are used will definitely affect the level of the treatment provided. So we very much need to work as a team, so the engineers can crunch the numbers, do the design, make sure they fit, etc., and that everything hangs together technically. But we need to work very closely with our landscape architect colleagues and rely upon their expertise to advise on the planting regimes, etc. In terms of siting of the inlets and the overflows, there's advice in the SuDS manual on the configuration of such things. If we're looking at a swale, this sort of top one here, that's up to sort of 20, 30, 40 meters long, what we're saying is the inflow entering into this particular system, we need to have the overflow fairly close to the inflow. When this builds up to the maximum design, you want that overflow to kind of trip in fairly soon. You don't want that down and too far away from the inflow. Same when you have the kind of teardrop shaped ones as well. You need to have the inlet fairly near to the overflow scenario and an overflow setup there. Typical examples of planting schemes are also contained within the SuDS manual. A great variety, depends on where you are. I mean, these range from Nottingham in the UK, London, and across to Portland, Oregon, west coast of the US, where we've got an office located over there. Interesting, you can see the inlet condition here is kind of wearing across through a drop curb. So I say you don't have to have like 1 in 3 side slopes. You don't have the space. You can just have slots taken out, build these into the highway schemes alongside a highway, etc. Typical planting layouts, shrubs and trees with occasional planting. We have the dominant local species, and then on the batter you've got the drier species coming up the drier slope. So you obviously need to be careful of what we're planting down here. It's going to be saturated from many parts, so often we're putting in salix, willow, things like that, that are water tolerant type species. So I'm no expert. Please talk to the landscape architects. Their invaluable expertise is used here. So with all that in mind, I'll now run through and give you a very quick demonstration of using MDSuDS and MicroDrainage. What I'd like to do is use MDSuDS in the first instance to identify the extent of that land take and the size of the structure based on those recommendations and guidances that are coming out of the latest Serious SuDS manual. We'll look at how I've designed a storage structure and better understand the flow through the structure itself to illustrate those benefits of reduced peak runoffs, etc. And then after that, I can show you how to introduce that particular structure into your greater microdrainage model. So let me take a look at my model in MDSuDS. I've actually run the analysis already. I'll just put it on the bottom toolbar and show you basically what I've done. I'll just zoom into one area. I've got the same model in MicroDrainage. So if I switch across to the MicroDrainage model, it's the identical model in MicroDrainage that I'm now going to show you in MDSuDS. Okay, so we load in a CAD drawing, can load in a ground model. All this information is within MDSuDS. I could show you the triangulation. We can deluge the surface, identify the outfalls, and we can identify the overland blue-green corridors, all within MDSuDS. So when you're scoping things out at the beginning, it's a great tool. And then what I've done on the right-hand side here, we have a range. This is a toolbox here. There are a range of drainage systems that we could incorporate within our models. So bioretention areas, bioretention with under drains, infiltration trenches, ponds, porous paving, etc., etc. They're all here. I've dragged across and dropped onto the model a bioretention area, and then I've just clicked to define the area that I have available. And that area that's available is now being shown here. So I'm double clicking on the structure, and if we look at the form, okay, if I click on the location, it's giving me the grid reference easting and the northing based on the CAD drawing. If we look at the dimensions of what I've set up here, there are two areas on the dimensions. On the left hand side, you'll notice that we have ponding area. This is that surface depression on the surface. So the exceedance level is essentially the ground level. At what point will flooding run across the surface of our development? It's when the water level reaches the ground level. So I have an exceedance level here of 32.584. The base level, if I open up the image, the base level is the base level of the surface depression. Okay, and I've set it 500 millimeters. As I say, they could be 150, 200, whatever. I've gone for a 500 millimeter deep depression here. The freeboard, I've set at 100 millimeters below the ground level. I want flood risk warning to come up when the water level is within 100 millimeters of the ground level. So I'm getting close to the ground. Because I've defined the area of the structure using CAD, it's telling me what the base area is in square meters. So it's 926 square meters. We've got 10,000 square meters in a hectare. So 8,000 square meters is 0.8 hectares. That's the maximum area getting into our structure from our development. But we've also got some characteristics in terms of lengths and widths and areas of them. So you have the actual dimension of the structure itself here and the length of it. I think in the earlier slide I mentioned 40 meters length was like a maximum. So you can just double check that you're somewhere there or thereabouts within the parameters of the guidance. The slope, this is the slope on the surface. I put it in really flat, 10,000, could put in 0 for like absolutely nothing at all. And because we're just outside of the sort of infrastructure, the highway, etc., there's a bit of public open space or open land here. So I'm going to let my hair down just because I can, and I'm going to put in 1 in 4 side slopes to have the runoff entering across and then into the structure. The top area is also being shown in square meters, so that's telling you the true land take at the very top of the structure around its perimeter. And we're being told what the perimeter at the base is, at the bottom of the slope, and the perimeter around the ground level at the top. Filtration rate going through in meters per hour, going through that subsoil. So we've got a soil condition here. What's the filtration rate through the soil before we enter into the media, the filter medium below? In terms of the filter area, we've got a base level right at the very bottom, down at 30.909, and you can see that I've incorporated an under drain. So you could either switch on or switch off an under drain. I've switched one on, and I've put it in at a 150 millimeter diameter. If we look at the filter layers down below the surface ponding, I've set up 3 layers. I could add or delete here. I can move them up, I can move them down, but I've added in just 3 layers. From the surface, the top layer down, I've got 375 millimeters. It's a sort of darker brown, 375 millimeters depth of sand, and then I've got 400 millimeters coarse sand, and then 400 millimeters of gravel. If I go on to the advanced, I'm saying there's no infiltration into the ground. We're in a clay soil, so there is no infiltration into the ground. We're just using this for attenuation purposes, both for the ponding area at the surface as well as the filter medium down below. If we were kind of punching through a clay layer on the surface, potentially you could switch on the infiltration through, say, the base or the side down below the clay layer, which would have maybe no infiltration through the side of the ponding area. If you knew that you had an interception volume, an additional volume available, you could sort of put that in there. That would be taken into consideration. I've set up evapotranspiration based on UK. We're getting 3 millimeters per day of evapotranspiration. That's the benefit, again, of having the green infrastructure within the basin itself. And here's a really interesting aspect. In future webinars, I'll look at other structures as well, such as swales. And within the guidance, we're being asked to retain the flow, delay the flow, hold it on the surface, slow down the flow. We're trying to reduce the peak runoff. We're trying to reduce the peak volume. So this delay time can now be modeled in MDSuDS. Here I've said 540 seconds. So I'm building in a 9-minute delay for the water that's run off into the basin before it starts to flow through the media. So we can model this more accurately now. We've also got a delay time that's automatically calculated based on those 3 layers by the program. Red means I've typed something in. Blue means that the software has calculated something for me. So the delay time going down through the filter media is being analyzed by the software, and the vertical retention time in seconds is being calculated. We're using Muskingum formula to do that, for those that are asking the question. I can hear Ludi typing in the background, so I'm trying to anticipate the questions for you. With regard to pollution, I'm just going to focus on the quantity today, because I know you've taken on board an awful lot of information already. We can also build in background concentration levels of a variety of pollutants that are running off into our structure. And then we can also model the filtration of the pollutants coming out based on the media that we've put into the model. I've left these blank right now just because I want to produce more models with more bioretention and other structures, link them all together in a SuDS train, and then share you the benefits that are coming from the water quantity, as well as those benefits that are coming from the water quality side, as well as this amenity and biodiversity enhancement as well. Have a look at a few more examples of what I'm kind of talking about on a sort of local scale. They can be these kind of things between the highway and an industrial development. So anyone working on commercial premises, industrial sites, business parks, things like that, often you'll see landscaped areas like this, and they will have a bioretention filter media down below them. So they're multiple benefit, multiple purpose kind of structures. Here's Joey here. You can see a little kangaroo. So some of the issues that they've had in Australia, washout, scour, when you have these like steep sloping sites, etc. They'll often put riprap in, larger stone, to prevent that erosion from happening. And again, you can just all manner of means down to like rain gardens, etc. There's many different types that we can look at. What I did, I ran an analysis with regard to the rainfall. I've just run the 30-year return period, and I've just run everything from like 15 minute up to the good old 7 days. So I've given this one a robust test. We can look at the results, and the results, we can generate a design report for the results. I've only got one system in the model here right now, so if I click on the summary of all drainage systems, it would just bring up this bioretention You can look at the results for all of the storms and identify what the critical result is, and we can look at the phase results for the critical. So I've gone through all of this, and it's the 30-minute summer event that's the critical one, 30-year return period. And we can see here through phase management what the volume coming into the structure is, over 200 cubic meters, but the volume going out. So the max inflow and the maximum outflow is all being calculated. With regard to the graphs, if I concentrate on the top one, this really is striking me as being the most beneficial in terms of the water quantity argument. So here's our total inflow, kind of peaking up at 200, just under 240 liters per second, and then draining down. That's the inflow. In terms of the outflow, this is the purple line. So you can see how the outflow has drastically reduced the peak inflow from down from just below 240 liters per second to 20 odd liters per second. If I switch that one off, I really like this result, because this is showing me the inflow volume, but also the total volume that's resident, the total resident volume building up. So that volume that's running off and has been building up in the system, yeah, you can see that graphically illustrated, as well as the outflow volume. So that's the one down at the lower level. And the lost volume. So what have we lost through evapotranspiration, this sort of depression storage evapotranspiration? You can't see that on the scale of things. So we get a benefit, but the benefit is quite minimal in terms of evapotranspiration, because I've only got 3 millimeters per day. When you get a very extreme event like the 30-year, there's way more flow coming because of the rainfall, and very little going out because of evapotranspiration. But if I switch off the inflow volume, and if I switch off the total resident volume and the outflow volume, it's shown on this, would you believe, but it's down at the low level. So I switch that off, and now we can see the lost volume, which is less than 0.01 of a cubic meter. But you're gaining a benefit. If you want to know how much it is, that's what it is. Okay. So if I close down those analyses, so what I would do, I might show you another one actually, because of the nature of the beast, I've added another one in here, which is a retrofit. So I've just zoomed in on the highway, and I'm thinking of the Rainscape projects as well. So where you're on restricted land uptake situations, I've added in a bioretention area here that I've retrofitted in effect. So if I select it and double click it, you can see I've got my length is 23 meters, so it's like 23 meters long, and I put in a side slope and of 1 in 4. I could put in like 0 slope there and have a hard edge actually, and model it that way with an under drain. So you can add these things all across your site, and then we could connect them. So it kind of leads on to the connections. How are these different systems connected? Well, they could be connected with pipes, with channels. You could just do a simple connection. If you want to look at the worst case scenario when you're starting off on the project, you could put in a no delay, and I could connect my retrofit, okay, across to the bioretention area with no delay in the flow between one and the other. So the outflow will instantly be an inflow with my downstream system. I could introduce attenuated flow, could slow that down. I could introduce lagged flow. So all these options are available. I've added in an inlet here as well, and I've connected it. So I've added an area of runoff. So the area is actually just over 1 hectare, and they're saying normally 0.8 of a hectare is the maximum runoff area that should enter into your bioretention system, but you could always try this and test it. How's the runoff coming into the bioretention area? Well, I've set it up based on time of concentration, but there are many different ways that you can calculate the runoff. You could use the flood studies report method, the flood estimation handbook, the revitalized RefH methodology, time area diagrams, Lawrenson or soil conservation survey methods. So there are different hydrological methods that you could use to calculate the runoff from a catchment entering into the system. I've used time of concentration, and it's telling me that it's taking 552 seconds for that runoff to enter into the bioretention area from the catchment. Okay, so we have the areas of runoff, you have the runoff entering into the structure. We could connect structures together. We can put in inlets. I mentioned the inlet being an important aspect nowadays. And if we put in a swale, for example, or that bioretention area down the highway, we can then model the lateral inflow entering into the structure. Or it could be point inflow, which is what we've typically been doing historically. We can add in rainwater tanks as well. And in terms of outlets, you can put in a range of flow controls, and if the flow control you're using isn't there, we can set it up as a depth flow relationship as well. So what do we do after we've modeled this, tested it, etc. in MDSuDS? Well, we can move over into MicroDrainage and look at our model. Within MicroDrainage, I've got the pipe network here, and I've added in flow control at the downstream end. And for those that are working with DrawNet, this is the easiest way to work in my mind, because you have the CAD drawing, we have the ground model, and now I can click on my toolbox, which is like really easy to use. Click on the toolbox, and when you click on the toolbox now with MicroDrainage 2015.2, if you've got simulation switched on and MDSuDS, we can now see that you also have FT structures, flow through structures. So you don't just design the pipes and the manholes, etc. with the flow controls. We can now also incorporate the flow through the structure. Now, here's the next trick that I think was really, really great that the development team put together. If I choose a bioretention area, so you can choose any of these different types of structure, but if I go to the bioretention area, I want to import the one that I've designed in MDSuDS. Normally, we've historically had to have dragged and dropped onto a manhole, onto a node. We use manholes as nodes for modeling purposes in MicroDrainage. Not so anymore, folks. What you can do is you can drag and drop the bioretention area, and you can drop that onto a pipe to replace the pipe. And this was like such a strong request that came through to enhance the visualization of the models and create a closer representation as to what's happening. And there you have the opportunity to import the structure. If you've designed your structure, a bioretention area in source control, as I say, you can do this in source control. You can load in your source control file, or if you're working with MDSuDS, because you're identifying these areas and lengths, etc., and that criteria in accordance with latest guidance, then I could choose MDSuDS, an MDSX file format. And if I just double click on my bio, it's now brought in the characteristics of that bioretention area that you saw in MDSuDS just now. I just have to set up with the flow through structure. They recommend the vegetative layer. What's the Manning's N of the vegetative layer? It's 0.035 is what they're kind of recommending. I don't have any infiltration, etc. And I've got the under drain information as well as the filter information. Remember those 3 layers of sand, coarse sand and gravel underneath the depression on the surface? And if I say OK to that, because we're replacing a pipe, okay, you can now see it's a double line with an arrow on there. Couple of things that's happened it's made the manholes look ridiculously big just to capture my eye, to say, look, you've dragged and dropped a structure to replace a pipe. So you now need to consider your model. So I might just go in and correct the manhole sizes. But if I go to my Blue Peter, because I'm looking at the time and it's running out fairly rapidly, if I go to my Blue Peter, what I've done, I've downsized my manhole sizes. The other thing that I did, I looked at the invert level because it would have taken up the slope of the pipe. So if I take a look at this in the long section view, these are all the upstream pipes and manholes feeding down into this, not a pipe anymore, but it's a bioretention area, which I've laid flat with that pipe and under drain pipe effectively connecting back into the downstream pipe network. So that's my model now created. Have a look at that on the plan view again. So you can see it's indicated by a double line with an arrow on it. So that's a structure now. It's not actually a pipe. I could click on it, right click, and look at the properties, and take a look at those properties of the pipe itself, and it's saying section type in the properties is bioretention area. So I could potentially click on pipes in the model and then select the fact that it's not a pipe. I could do it directly here and say, no, that's a bioretention area now, not a pipe. Other options for you to try and help improve your productivity and compliance with the local needs. And if I may go back on to, say, 3D, we can see within the 3D model, the pipes shown as a grassy bioretention area. And you have all the network underneath. And then what I'd do is I'd go to my wizards and I'd go through my normal auditing process with the bioretention area incorporated into my model. I drag and drop the retrofit one in the highway, etc., etc. I think you've got the idea.
Peter, we have a question.
Okay.
For those using older versions of Windows, could a bioretention unit be designed using a head-discharge relationship, which represents a filtration rate for the combined soil layers? So basically the question is, what is the difference now from what it was before?
Yeah,
what is
the
benefit?
Benefit now is that if you use MDSuDS and MicroDrainage, so the question was, if you had an older version of MicroDrainage, could you model a bioretention area by setting up like a head flow or something like that, maybe building in lag times for time area? Doable, but the benefit of doing it in MDSuDS with MicroDrainage now is that when you set up those parameters, we know permeabilities, we know porosities of these underlying layers, and the program itself will use industry standard formulae, Muskingum, Mannings, things like this, and it will then identify the flow through this. It will calculate the flow through the structure for you. The other benefit is just visually, I'm using MDSuDS to scope out the base and the top areas of these things. So when I'm trying to convince developers that it's not taking up a ridiculous amount of land and I'm fitting them into like gardens or highway schemes as retrofits, it's just the visuals I find compelling and helpful because I'm working within the CAD environment. So I think it's really helping to prove the case to the clients as well as the approving authorities, and I'm getting the program to do the number crunching for me. So I hope that was helpful to show you the multiple benefits of working with FTS, flow-through structures. It does help to reduce peak runoff rates. It does help to reduce the volume of the runoff. Great for water quality and pollution control, and really good for the amenity and biodiversity, the 4 pillars that we discussed at the very beginning. I love the fact that this isn't something that's like pie in the sky for the future, but there's £15 million worth of projects delivered in Wales retrofitting things like bioretention areas and swales and things like that. So it's happened. It's not happening. It's actually happened. And kudos and congratulations to everyone involved over there, by the way.
I just wanted to mention that we received many questions, and unfortunately we're running out of time, so we will reply to you individually via email.
Oh, cool. So Luda's just said we had loads of questions. I've heard her tapping away furiously. So we will be providing answers individually, and we can share them as well if everyone's happy with us sharing the answers to the questions that were raised. Just looking ahead, because the clock's ticking away here. Sorry, folks. But over the next month or so, we've got next 2 days, SciWem annual conference in London. So come along, see the guys there. Mike's going to be there, I believe, Mike Reeves. So come along and say hi to Mike and the team at the SciWem annual conference. Ludi, sat to my left, will be running XP Swim training next week on the 26th to the 28th. 3 days of great training there on modeling, folks. So if you've been suffering from any kind of flooding, blocked culverts, looking at impact of new developments upon the existing regime, Ludi is the girl to talk to, and look at coming along to some XP Swim training to cover all of those kind of aspects, linking the 1D existing models with the 2D overland flood flow routing. And then 16th to the 19th of May, we're running training here, MicroDrainage training, courses A and B, which are like run every month. They're so popular. And then F and G, F being the SuDS training course and G being more the hydrology training course. We've got an MDSuDS training course as well, by the way, folks, but that'll be run the following session in June. And yeah, put a note in the diary, 19th of May, Magic Day. It's my birthday, so I think I'll be training that day, but all good fun. And look forward to the next webinar, which will be on Wednesday, the 25th of May, where I'm going to be a year older. And look forward to any suggestions on what you'd like to see. I'm thinking of building up a SuDS treatment train and looking a little bit more at those pollution aspects. There is a chapter in the SuDS manual on water quality and pollution that's worth covering. And do tune in to Mark Goodyear's excellent presentations and webinars on the new Serious SuDS Manual 753. So go take a look at Engineering Nature's Way. Engineering Nature's Way, and you'll be able to book yourself to register for those webinars. And yeah, well done, Mark. They're really great and informative. Thank you all for your questions. Look forward to receiving your feedback and look forward to engaging with you again at the next webinar. Take care, folks. Thank you, Ludi.
You're welcome.
Have a great month. Bye.
Bye-bye.